So I've actually just migrated this to the latest 0.18 patch. I am hoping that nothing has really broken here. All we really care about is our science. Blue, black, green, yellow, red, purple. Or is purple not currently? Where is... Oh, there's obviously some sort of supply problems. Logistically, military science is the problem. Military science. Military science. Ooh, the other thing I want is analytics open. Military science. I probably put that after. Yeah, here it is. Military science. Certainly looks okay, but we're obviously missing something. Plenty of coal. Plenty of stone brick, although it's using stone brick at a prodigious rate. Am I going to run out of stone brick anytime soon? Oh, yeah. Yeah, I am. I would say that that is probably the main reason we're losing out on military science. Yeah. It's a pretty good game. By the way, if you don't know, this is Factorio. And I swear it's not just because I wanted to play Factorio today, it's because it's directly linked to today's lecture. So this is a mega base I've been working on for some time. Launched plenty of rockets. I've left it running for many, many hours. You can see that I've been trying to get up to 2K science consistently, and it's almost there. I mean, I'm almost, but there are definitely some problems with the supply. And so I'm just, this is the first time I've been back to this base in quite some time. So maybe I should actually figure out what the heck I'm doing here. So this is just making speed 1 modules. This is just making rocket control units. And then here's where I actually make my white science, or rockets, whatever you want to say. Now, I guess a question is, where do I make stone brick? Looks like I make stone brick here, and only here, it appears. And that doesn't seem to be enough to load up all the time. Oh yeah, the biters are, geez, this map is so big, even auto-saving takes quite some time. You can see my turret coverage. Hey, where are my turrets? Oh no, that's my pollution. My turret coverage is keeping the biters at a healthy breathing room. I got plenty of space. There are times that I definitely don't enjoy playing with biters, but they're not really going to get through this wall of laser turrets. So what was I saying? Oh, the stone brick seems to currently be the problem I'm tracking down. So here's a train, and the problem seems to be that I do not have enough coming into here. I certainly am making tons of stone brick, but if I look here, I can actually see that we are not operating our miners at full efficiency. So maybe what I could do is just go over there and add another lane. So one of the things about this playthrough is I have quite a few blueprints that I use. This wonderful train station based on one I found online, but I've tweaked a little bit to make it line up with all of the blocks. Am I going in the right direction? Yes, I am. I really should lay down some concrete walkways here. Okay, here we go. So it's clear that we are not using all of the resources that we could. There's lots of slowdowns. You can actually see that things are not going in as fast as they might otherwise. So let's try, gosh, I really want to put it on this side. Probably it'll be a little easier on this side. We'll have to move a few things around. So let's go to my smelting blueprints, which are not mine. I just use them. So I'm just going to plop that down and let it go. I've got a large enough network that all this is going to get plopped down pretty much on its own. But what I want to do here is, let's see, I want to get more stuff into this at a time. So like that's not moving at all. So I could say, hey, let's put our output priority on the left. This is not ideal, but let's take that over there. Let that go in. Did not even slow it down, did it? Hopefully that will. All right, so while the robots are constructing that, we'll take this here. And I'm just going to bring a third lane over and load it up into the truck. Oop. Because we need a little bit more. We need a little more stone brick. It's not going to run fast yet, but we obviously have enough to be building it. Let's see, how are the rest of these going? This one looks like it has a little bit of longevity left in it. So why are we playing this today? We're just about to start class. How many folks do we have? About half the class. We're talking about this today because this is an excellent way to start a conversation about coupling and cohesion. Because this is a base that is not, it's not terrible. I'm pretty happy with it. It's not quite where it needs to be, but it's close. Waiting for space. Yeah, see, it's still going pretty fast. Might be able to do something a little more with this, but hopefully that will take our stone brick production and really ramp it up. If we just watch stone brick. Oh, isn't there a new? This is still the old one. That's weird. Used to be a search bar for it. Stone brick. So we have definitely taken our stone brick production, which has been constant for quite a while in terms of our usage, from 4.6, and we kind of leveled out at 7.6. That's like a doubling. No, I am not brave enough to play Bob's Mods or Crestorio or anything like that. This is just vanilla with a couple of mods, a couple of quality of life mods. And actually, logistics train mod is enabled, but I'm not actually using it. I'm using some blueprints for easy train stations or easy train network. So it's actually not a global train network. It uses some fancy combinator logic. So I seem to have pretty good. I'm going to take this like this and just take the last of it out of here. That should be enough to give me an extra 2 full belts. But I will say, let's keep the stuff going into the main one first. Only give me the leftovers. This should turn everything on at full, I think. So that's everything. Geez, going about, it's still actually a little bit backed up. I'm impressed. Okay, so why are we here today? Before we get into the lectures, just thought I would start here because this is kind of where we're starting. What is the name of this game? This is Factorio by Wube Software. It's Steam. It's actually quite impressive. You can actually build digital logic circuits inside of this with there's a lot going into this game. But the basic goal is you need to launch. Where's my rockets? You need to launch rockets. This is a rocket station. I'm actually surprised that it's not. Oh, I'm short on a particular thing. It's a game where you build up a base. You start basically with a pickaxe and you build up. So this is a base, and I thought I would take you on a little bit of a tour of this base because it's a good primer on what we're talking about today. So this is, geez, where to start? This is a game about building things and making automation happen. But what you'll see is a lot of repeating patterns. Like this right here is a solar panel array. And there are parts of it that are a little bit modified, but for the most part, you can see that pattern used over and over and over again. And I use blueprints to stamp this down. And if you look over here, this is actually a nuclear power generation facility. So a bunch of nukes go and they produce steam, and then the steam goes into turbines, and the turbines generate electricity that powers everything else. Now, all the gray you see is train tracks. This is how I get stuff from one place to another. You can see there a train going along, and I think it's going to go and get some green circuit boards. So for those of you going to take ECE388 or have already taken ECE388, let me show you where I make green circuit boards. Right here, green circuit boards. This is only marginally. I don't want to spend too much time on this, but while we're waiting for everybody to kind of get here for class, we still have some folks. The reason I'm here is because there's two kinds of ways to play Factorio. One is a very ordered, structured way, where everything is sort of square and tiles out and things like that. And I have a lot of that. You'll notice this is an extremely repeating pattern that I use to make red circuit boards. Green circuit boards are made over here, red circuit boards made over here, and then blue circuit boards are made over here. It's all very structured, very tileable. That's one way of playing Factorio. The other way is over here. This is where I started my main base, and this is what is colloquially known as spaghetti. Because all of these belts that transport materials from one place to another just kind of go in and out, and they weave under each other. Like, what's really happening here? I'm taking some stone and some stone brick, and I'm putting them onto half a belt together, and then I don't even know what's happening here. I'm taking some iron plate from one place, moving it to another place, and then moving it further on down the line. And God help you if you try to figure out what's happening in this section. Yeah, this is Factorio. And the reason we're talking about Factorio is because this is harder to fix, sort of. So this is a base that's going on, and while we were starting, we had put in some more stone brick, and I think this might actually be enough to keep our military science production, which is all the way over here. Yes, we've got some military science going pretty well right now. And I'm currently researching artillery shell range 11. So I think that our stone brick problem has maybe been solved, but not our low density structures. Yeah, our low density structure belts are completely empty. But I'm able to make that assessment because I have created this in such a way that, well, everything is sort of separated from one another. Each one of these, if I actually, yeah, you can see the names of my stations. This one is for unloading rocket fuel, unloading lubricant for motors, low density structures, blue chips, batteries, sulfur, red chips, green chips, coal, brick, stone, steel, copper, iron, and gears. So everything has its place, a place for everything and everything in its place. This was where I started, and it's much less helpful, actually. It's quite a bit difficult to see what's going on, although to some extent there are definitely some things going on. So if you do play Factorio and you guys have suggestions for this base, feel free to leave them in the comments. But very generally, I've got oil down here. Oh, no, apparently I have steel down here. That's extra steel. Oh, yes, it is extra steel. And the goal is to basically mine this patch out. So how does this relate to our lecture today? I'm sorry, we can't play Factorio all hour. Quit. Actually save, because we did make some changes here. How does this relate to, nope, not computational complexity, to cohesion and coupling? Cohesion and coupling. You should play FIFA. What is that, like a buffer? Like a first in, first append? Cohesion and coupling. All right. So these are two words, and these two words separate good programmers from bad programmers. Okay. It's a soccer game. Yeah, no, I'm not going to play that. Cohesion describes how you guys didn't even think my joke was like first in, first append, like FIFO, or like, never mind. Cohesion describes how closely all the routines in a class. Wait, hold on. Do I need to use this microphone or this microphone? That microphone. Okay. Describes how closely all the routines in a class make sense to be there. If you have everything, you throw everything into a particular class, that's bad cohesion or weak cohesion, because things in a class aren't really related to one another. So you want strong cohesion. You keep everything that needs to be there, but nothing else. This is the chili palma of programming. Say only what you need, if that. If you don't know who Chili Palma is, early 90s movie, 91, 92, Get Shorty, also starring Danny DeVito. Chili Palma, he's a Shylock who goes looking for some money. Actually, who is that? James Woods? Is that James Woods? I think he goes looking for James Woods. I'm afraid to find out what that subreddit is. Okay, the reason we talk about cohesion and the reason we want strong cohesion is because it really makes your program more easy to update and maintain. Just like my Factorio, when I needed more steel, I just dumped another steel thing in there, put a station, and steel started coming into my main base. You saw me at the beginning of class just throw down an extra blueprint for smelting stone brick. And suddenly I almost doubled my stone brick from 4 point something to 7 point something. Okay, so good and bad cohesion. Good, hard disk. Everything you need to access the data on a hard disk is right there. You just connect to it. You put one connection. Bad is spaghetti. Okay, it's very difficult to pull one strand of spaghetti out without dealing with every other piece of spaghetti. It can have unintended side effects. And that's what we want to avoid. We want to avoid this complexity of everything is resting on something else and relying on something else. We don't want that. We want to just be able to take a piece, drop it somewhere, or move it somewhere, or reuse it. So the STL, not the STL, that's a C++ thing. The .NET framework is a great example. The math class, that static class, has methods related to math. Anything you really need to do mathematically, you can find in the math class. Sine, cosine, your tangent. And then more basic like square root and power, as well as some commonly used math constants, pi and e. But everything lives inside of math, okay? So if you're trying to do some sort of trigonometric thing where you find whatever you like, the area of a particular thing, you can do that using just calls to math. Okay, bad cohesion. We don't have like public examples of bad cohesion, although I'm sure if you go on GitHub, you can find people doing bad things. But let's take a class called Magic, okay? And the goal is to deal with documents. We're dealing with documents that we have to send to other people or to a printer. So, okay, we've got a document class D, and we can print that document. Print document sends it to the printer. So you give the document D to print document, it prints it out to a printer. However that complexity is managed, however you actually render it, get it to go over the network or over the USB, fine, all handled. That's great. Sending an email, sure, you send a recipient, a subject, and some text, okay, but sending an email isn't sending a document. It has nothing to do with a document. Maybe you could make a case that you have attachments, but that's not listed in this prototype. And certainly calculating the distance between 2 points has nothing to do with printing a document. But if all of these were in the same class, we'd call that bad cohesion. the things don't really make sense together. It's like the feng shui of the C# or the programming world. You want things that make sense to go together and things that don't to be completely separate. Okay? If we look at another class, something that says make a pizza or withdrawing money, what would withdrawing money be from a bank account, maybe? I guess technically you could make a case that in order to buy the pizza, you need to withdraw money, but that's a bad example of cohesion. You should abstract it into two separate things, okay? One thing makes a pizza, one thing handles transactions, okay? Opening a database connection has nothing to do with making a pizza, except that it might be somehow dealing with getting access to the financial data to pay for the pizza. But again, those three things should really be separate, their own classes. Okay, so coupling is the second vocab. Three vocab words today. Cohesion and then coupling. Now with cohesion, you want tight cohesion. Everything that it needs to be should be in one class. Coupling is the idea that multiple classes can be well defined in their interface together. Okay, you don't want to have methods that need internal data from another class. So either you should use public properties to access that data when possible, or some other programming method. So you want modules or classes to depend very little on one another, except for some small interfaces between them. You also want the routines in the class to do very little. And when I say very little, I don't mean they don't do a whole lot, but they do only what they need to accomplish their task. Okay? You want to design a class to be standalone, could be used anywhere. Now, you guys are all working on your final projects. You have an end goal. But if you work with the idea of loose coupling, it's going to be a lot easier to expand your program further on down the line if you need to. Okay, so take for an example any hard drive. I usually keep one or two around on my desk. Okay, here's, looks like a spinning 1 terabyte Western Digital Black 2.5-inch drive. There it is. Oh, that's very difficult. It's showing up behind. It's very strange. Believe me, I promise it's a Western Digital Black. But the key thing is the connector on the end. Does anybody know what that kind of connector there is called? That's got a very specific name, and it's standard across all computers made in the last decade, 2 decades. It's a SATA connector, or SATA connector. Yeah. ATA isn't enough because there's 2 kinds of ATA. There's parallel ATA and serial ATA. I don't know if I have a parallel ATA or an IDE connector. But this is serial. It actually communicates serially 1 bit at a time. But to replace this hard drive, I think this used to be in one of my laptops. To replace it, I unplugged the power and the SATA, and that was it. So that 3.5-inch drive right there uses the same connections. It's using actually a fairly old power connector on the left side of the screen, and then the data is that red cable. Okay, so I could take this drive, stick it in to whatever computer is using that hard drive, and I'd have a new hard drive that I could use. Easy to replace. And that's good, because if the hard drive fails, you can replace it. Now, that's a little bit different when we start talking about another piece of a computer, the motherboard. The motherboard actually has very tight coupling. So in a motherboard, everything has to be on the same board. We don't really do things where you have a little piece here and a little piece here and a little piece there. Because of the high-speed nature of it, you need to have your PCI lanes headed directly into the processor. You need to have the right footprint for that processor. The memory is DDR4, DDR whatever. So it all has to be on one board. So imagine that you wanted to take, by the way, does anybody know what that purple connector is right there? This is a fairly old photo. Has anybody ever used that purple connector? It's a parallel port. It used to be called a printer port. 25 pin. Yeah, it is. Imagine you wanted to change that port, something was broken, a parallel port was broken. What are your only options for replacing that? Are there any options for replacing that? So it breaks. Either you jam a pin in it or something falls off of it. The only option is you have to get out a soldering iron, manually desolder that connector, all 25 pins at once, and pull it off. Mostly though, yeah, you're right, a new motherboard. Imagine that. One parallel port's broken and you throw away the whole motherboard. That's tight coupling. Now, the advantage is everything just works on a motherboard. But that's kind of a downside too. There's no real repairability. Now, maybe the parallel port, that's probably the easiest thing to repair. Imagine if, I'm going to assume that this right here is some sort of graphics coprocessor, maybe. We could look it up. That part number is almost readable. Imagine if that broke. Good luck resoldering that ball grid array chip back on there, if you can even find the chip. Okay? But that's an example where tight coupling is actually okay because the block itself is loosely coupled to all the other pieces. You have your PCI Express slots, okay, but internally you have very tight or strong cohesion, okay? So this is technically tight coupling, but it's also strong cohesion because we look at the motherboard as a unit. As you say, you replace the whole thing. So you pull that motherboard out, you stick in a new motherboard. You can probably take a lot of things off of your old PC, take out your graphics card, take out your Ethernet adapter if there is one, take your processor out and put it in if it's the same socket. Okay, so that's what I'm trying to get at when I talk about coupling and cohesion, two different things. So let's take a look at this class. We've got a class called report, we've got a class called printer, and a class called program. Okay. This is loose coupling. Notice that the class report, what other object types does this rely on? It relies on bool, which is a built-in type, and string. But it creates an instance of a report. Printer relies on report, but only as an argument into the function. It doesn't have to get access to any of the internals of report. It doesn't have to, for example, it doesn't say print, take a file name, and then call load from file. It doesn't do that. It takes a fully fledged report. It's up to the main program to create the report, load it from file, and then print it. This is loose coupling. Report doesn't rely on printer. Printer does rely on report, but that's allowed, okay? The whole point of a printer is to print reports in this example, right? So it keeps everything loose. So any report or anything that inherits from report could be sent to printer. Okay, here's tight coupling. Well, sort of a contrived example of tight coupling. Math parameters, an operand and a result. So some number and some result based on that operand. Then we have a math util that calls calculate square root. Okay. Calculate square root operates on math.operand. This is like insane. First, you have to take a static method or static property and assign it a number. And then you call square root with no argument, and then you get the result in a separate object. So in order to calculate the square root of a number, you assign it to something that has nothing to do with the square root function. This is like silly. It's extra silly. Okay? So you have this class that just holds numbers. That's all it does. It doesn't know what those numbers are going to do. It doesn't have any real control over those numbers. It's tight coupling and it's bad. Don't do this. Okay? Obviously, you could write a method that would take a number in for square root and calculate the square root of that number. It's actually built in, right? So let's take a look at a couple of things. This is a great example of spaghetti code, just like my starter base there that had spaghetti lines of belts running around. Here we've got a class called report. And you look at it and say, okay, maybe you want to be able to print the report. You want to save the report. But then it starts getting a little bit more confusing because you can load the printer driver to print the report. And then you've got a class called printer that loads the report and checks the report. Wouldn't it be the report's job to check the report? So this is sort of an impromptu code review. A lot of these should be swapped in terms of where they go, because the printer is relying on, the report is relying on the printer to set the file name of the report. The printer driver is being loaded in the report. You would think the printer driver would be in the printer class. So this is bad cohesion and tight coupling. Bad cohesion because the printer and the report aren't separated. Okay, the report stuff is sprinkled in amongst the printer, and the report class has bits of the printer inside of it. Now, that doesn't mean this doesn't work. You can write code and you can make it do all the correct things. That's not what this lecture is about. It's not about can you make it work. It's about should you do it. And you should not do this. Yes, you could make this work by basically writing around the bad code. But that's not a good idea. It's a waste of your time, and it's not going to produce high quality, well-maintained code. Okay? So this is actually, I think, one of our last lectures we did. We talked about polymorphism and juggling, right? So object-oriented principles, inheritance, the idea that you can have classes that inherit both fields, members, and methods from a parent class. Encapsulation, keeping all of the data separate. Abstraction is what we just talked about, keeping things simple and together, not allowing access to things that other classes don't need access to. Okay. And polymorphism, the idea that if you have a parent class, you can iterate over lots of different types of subclasses all in one loop, just based on their reference. So if you can practice keeping strong cohesion, just the pieces you need inside of a class, and loose coupling, and the hallmark of loose coupling is the interface. Okay, you send in external data through a known interface. Here, the print method prints the report of type report. Okay, now the printer might also have some information about loading the printer driver and things like that, but the report never needs to know about that. The printer just needs to be able to parse out the data in the report. Okay, so this is more of a warning as you begin your final projects and you start. If you can plan out your final project and what it might look like, or at least create some dummy classes that you then define some interfaces to, okay, you are going to actually not be wasting your time. Even though you're not sitting down and programming right away, you shouldn't. Start with either a piece of paper, draw some UML diagrams, define how your classes are going to look, okay? That's going to be a lot better use of your time than trying to code and code and code and putting spaghetti code together, okay? I'm going to load up another lecture here, but throw comments and questions into the chat. No questions so far? Okay. So the next thing I want to talk about, we just talked about do's and don'ts when writing large code bases. Another thing that you might do is you might actually do some analysis on the code that you've written. And we've touched on this in a couple of different ways as we've been talking about things. I often talk about doing a linear search through a list. And that's only part of this. So we're going to talk about algorithms, complexity, and efficiency. Oops, this is gonna. There we go. So I think even if you're an electrical engineer and you're never going to code ever again, you should pay attention to this because it doesn't just apply to your programming career. It applies to everything. How complex something is and being able to describe how complex something is going to hold you in good stead. So we have two general cases in computer programming we care about. The time complexity, meaning how long something will take, and the memory complexity. On your exam, you had a question that said, concatenate two strings, but do it the fast way. Don't do it the slow way. And the way I tested that was I didn't just try to measure the number of microseconds that it took to add two numbers together. I took a small string, and I put that small string together with it. So that created a bigger string. And then I appended something else onto that string. And then I appended something else onto that string. And in that idea, I did it, I don't know, 10,000, 100,000 times. Go ahead and look at the tests, because I just run it a zillion times, and I look at the average time. And I did some sort of a baseline of how many milliseconds it took. If it was over this much, you got partial credit for doing it the slow way. If it was under this much, you got full credit for doing it the fast way. So being able to recognize the difference between a slow algorithm and a fast algorithm is part of your job. And we also have to take into account the idea that there are going to be average run times and then worst case run times. And when we are programming, we almost never look at the average time, because Murphy's law says that in the time where you really need it to run fast, you're going to get the worst case input. And also, how do we identify what the worst case input looks like? And to this end, we're going to be talking about arrays versus lists versus hash tables or dictionaries. And how and when do you choose those? So we actually did a little bit of this last week when we were doing our implementations. Okay, what's going on here? Okay, ooh, too far. So why are we talking about data structures at all? What is a data structure and what is an algorithm? A data structure is just a way of holding on to data. It's, in our case, a class. But an algorithm is just a way of doing things, a set of instructions. Okay, so everybody who's taking this course should at least know how to create and use things like an array of type whatever, a linked list, a stack, a queue, a dictionary, and then perhaps sorted dictionaries. Because each of these has strengths and weaknesses, and we can evaluate, back one, what's going on here? We can evaluate their time and their memory complexity in the worst case, okay? So let's talk, how do we talk about a complexity? Well, generally we talk about its asymptotic notation, the asymptotic notation. And what that means is, as the number of items approaches infinity, so say we're trying to find something in a list, how long will it take? So if we're doing a linear search through an array, right, we have a constant time access. We're just moving a pointer along, so it's constant time there. And then we have some number of comparisons. Now, if I've got a deck of cards, I've got an imaginary deck of cards here, here it is, and I've shuffled the imaginary deck of cards, here it is, and I want to find the ace of spades. And I find the ace of spades by taking the top card off the deck, looking at it, and if it's the ace of spades, I'm done. And if not, I put that down on the table and I look at the next card. How many cards will I have to look at before I find the ace of spades? It'd be a lot better if I had a deck of cards. I'm going to look for a deck of cards. You think about how many times I'm going to have to look at cards. Put your answer in the chat. Come on. I have a box of computer goods. So maybe I need to find a SATA cable in this. There's maybe 50 cables in here, and the first one I pull out is No, that's for a power supply. This is a Molex power connector. Molex power connector. Ben, that's a great answer, actually. Minimum, once. Maximum, all of them. So, in the best case scenario, it's the top card. So I have to look at one card and I'm done. At the worst case, I'm going to have to look all the way and it's always going to be at the bottom. So, a lot of you have, that is a random variable. That's a very Professor Zing thing to say. A random variable. That's right. So what we say is that on average, we're going to have to look through 26. Because on average, we'll get the best case about the same amount of times we get the worst case, and then everything in between as well. So we say that the best we can do is half of the maximum. So one half n. And we can do this not just for the time, but for how much memory it takes. For example, how many cards do I have to keep in my head at any one time when I'm trying to find a particular card? Do I have to keep the whole deck in my head? Do I have to keep half the deck in my head? Does it change based on how many cards? Well, in the case of a linear search, you only have to look at the card in your hand. So that's a memory space complexity of 1, or constant time. But a computational time of half n, where n is the number of cards. So if I had a 6-card shoe with 6 decks in it, I'd have to look 6 times 52, call it 312, so about 156 cards in order to find that. Don't quote me on the math. Excuse me. So we talk about the total number of primitive steps to execute something. So in this case, it was the number of comparisons that I was looking at. So we can measure things like time, and we measure time not in seconds because my computer is going to run faster than your computer or slower than your computer. So we talk about number of steps or number of operations. We could break that further down into network complexity or disk I/O or things like that. But in general, we care about the worst case. Now, let's take that search example. And we said for 52 cards, it's going to be 26 operations. For a 6-deck shoe, it's going to be about 156 operations. For a 100-deck shoe, it's going to be 2,600 cards, right? 52 times 100 is 5,200. So yeah, 2,600. So let's say we have 1,000,000 decks. It's going to be roughly, well, it's going to be less than 1,000,000, right? It's going to be basically 1,000,000. What if I say 1,000,000,000,000 or 1,000,000,000,000? At that point, we're still in this range where is the difference between half a quadrillion and a quadrillion really that relevant? No. So we talk about asymptotic complexity. And what we're saying here is that we care about the upper bound of the most significant term. And when we talk about the most significant term, we care only about its power. So in a linear search, the power of n is 1. It's n to the 1. Now, take a different problem, same deck of cards. We're back down to 52 cards. How many comparisons or how many steps would it take if I took the deck of cards, threw it up in the air, it all landed on the ground? How long would it take you to put that deck back in order? And actually, in the chat, tell me how you would do that. Or, algorithmically, what would you do in steps to keep your personal time to a bare minimum? Think about that and type that in. Because we're talking about our worst case, our average case, our best case. So for you, trying to do a sort on a deck of cards is probably your average case. They're going to be mostly out of order in a random way. You won't be able to infer any data from that. But it's possible that I take that deck of cards, I throw it up in the air, it drops on the ground exactly in order, just somehow magically. So the worst thing that you would have to do in the best case is just actually look at each card, and yes, it is in the correct order. That's a pretty good way of doing it. Organize, suit, then value. So you make 4 piles, and you just go through the deck once, and you create 4 piles, and then you take the first deck, which is maybe just clubs, and then you sort them by value. And how do you sort them by value? For the least amount of time, grab all of them and make them neat. What, like a scotch? Make them neat. So the sorting then becomes an operation that you do a bucket sort. Okay, all right, that's maybe not necessarily clear to everyone. Anyway, I think we've already established that there's a couple of algorithms you could use just based on your idea. So how do we evaluate them? So let's go back to this case of a sequential search. Okay, let's formalize it. The worst case, we have to do n comparisons. The best case, we find it at the first. And our average case is n over 2. So that's 1/2 n. We say that this runs in linear time. Okay, because if you take, can I do a little, hold that thought for just a second. I want to do a little, oh, can I, oh no. Can I do it like this? Comment. Yeah, that'll work. Okay, so here we go. Ooh. Oh, this is not working well. 1/2 n. When we say 1/2 n, that's n is the size of the deck, that size there. And the average case, this is the number of worst case or the longest operations. So the operation we're doing here is a comparison. We have some number that we care about, x, and we look at each of these and we say, is this equal to x? No. And then we look again, is this equal to x? So our operation is a comparison. Okay. Now, technically, we're doing a lot more than that. If you've taken 263, you've gone line by line and figured out how many cycles some things take. But in this case, it's n or somewhere between 1 and n operations for a size of n. That's linear time. So as n approaches infinity, your time approaches 1 infinity. And we have to, I know infinity you can't have multiples of infinity, but we're going to talk about 1 infinity. And we call that worst case operation big O. Okay, we call it big O notation or asymptotic notation. So we say big O of G or big O of n is linear time. All the elements they're looked at once or a multiple of once. And we drop the coefficient. We drop the coefficient because in the long term, whether you do 1 infinity or 2 infinities, it's not really that relevant. What's really important is the power that you raise that number to. So 1 infinity is very different from infinity infinities. You would agree. It's very difficult to go from 1 or 2 or 10 or 100 infinities to infinity infinities. So quadratic complexity, that's very bad. And we've seen some things that might be that type of complexity. Things like a bubble sort, okay, is a quadratic time. In worst case, you have to look at every element n times. Okay, so we call that the big O notation. There exists a positive constant c and n such that, yes, all we're saying here is that anything down here, okay, is reduced. So for a theta notation where the theta is bounded by 3n squared plus n over 2 plus 12 operations, that 12 just doesn't matter in the asymptotic land that we're headed to. It doesn't really make a difference. When we're trying to compare algorithms, we care only about the first term, the highest term, n squared. So we say, it doesn't matter if we're doing 3n squared or 4n squared, they're about the same, because we're talking about the worst case. Okay? Now, most times we won't actually get the worst case input. We'll get an average case input. So maybe they'll be roughly the same. When we look at other things, here's one that's 4n times the log base 2 of 3n plus 1 plus 2n minus 1. Okay, well, I suppose you could take this 2n minus 1. You could do a little bit of math here, and you could move that 2n into this. My purple shirt? It's a good shirt. This is from C-Lab. This is a New Bedford native summer camp that I went to, gosh, before you were born. If you've ever heard of C-Lab, leave a comment down in the description. Great program. 4n log 2. So we ignore the power of the logarithm because in the grand scheme of things, logarithms are logarithms. Okay, so we care only that it's some n times log of n, which is still pretty reasonable because as you increase, it's almost linear, but it's certainly not quadratic. Okay. So 3 common things that you'll see. Constant notation means that no matter what, it is always done in the same amount of steps, regardless of how big the input size is, done in basically the same amount of steps. Logarithmic, log of n. So if you increase your factor by a power, you go up linearly. Okay, so a lot of binary things are log n. Okay, so if you double your input, you only add 1 extra step. Things like trees. So if I take, and I am somehow representing my information in a binary tree. Here I've got 3 things, and so I have to traverse 2 levels. If I double that number of things, I add another 4 things. In this binary tree, I've only added 1 level. Double again. I've only added 1 level that I have to search. So things like that, logarithmic time. For every doubling or every multiple that you do, order of magnitude that you go up, you're linearly increasing the number of steps. And then linear time. If your input size increases by 10, your overall worst case will increase by some multiple of 10. Then we get to the not so great ones. Quadratic. If you double your input size, you quadruple your time or your complexity. If you quadruple your time, you multiply your output time by 16. Cubic is even worse. Double your input size, multiply your output by 8. And then factorial and exponential, it's just give up. Those aren't great routines. Now, sometimes you can't avoid that. All right, you have to use those. But you want to avoid those when there exists an algorithm that can do something in constant or log or ln time. Avoid exponential routines when you can. So just to give you an idea of how much this becomes a problem for certain complexities, right? So some size, some input size n. Constant time is always going to run immediately. Log time is generally, until you get several orders of magnitude, it's going to run pretty constantly on modern processors, right? So this is a sort of an exaggeration. But when we do things that are n squared, after a certain time, it starts becoming a problem. Does anybody remember what problem I showed that we demonstrated like 2 seconds or less than a second, 2 seconds, and then 3 to 4 minutes? Does anybody remember what lecture that was from? I demonstrated something that had n squared time. And now if you start talking about n cubed time, just give up, okay? Where it says hangs, you can think of those things as basically not going to complete before the heat death of the universe. So even just going from 10 to 100 for n factorial times, it's not going to happen. So avoid routines that do that. Imagine something that in complexity of just 10 items jumps to several minutes, and doubling that basically goes on to a point that is not possible. Yes, that's right, string builder. With string builder, and well, not string builder, but strings, immutable strings, when we did concatenation, we saw that just adding letter by letter with strings took many minutes, whereas with string builder, which worked much faster with either a constant or a linear time, was much, much faster. Okay. Okay. So when we start talking about, and again, this is a little bit beyond the scope, but just to let you know that this does exist. In more complex problems, you will actually see multiple variables, multivariate asymptotic notations. So if you have a matrix that is of two different sizes, a square or a rectangle, sometimes you'll see it written as n times m. Some will just say, all right, we're always going to assume a square, so n times n, you might as well assume is n squared. Okay. When you have a depth first search traversal of a tree with n vertices, m edges, it's a linear time algorithm. You're taking two integers, adding them, you end up with an integer, not a power. Okay. Now, so far, we've only been sort of considering the time complexity, but memory complexity is a thing. And in fact, you've already shown me that you understand about memory complexity. The fastest routine I saw for sorting a deck of cards was to create 4 separate piles. So you actually had to take all 4 piles and have a space for them. You can think of them as spaces for 4 cards or 4 decks of cards. So you created a faster runtime by using more memory. And that's a time-memory trade-off. Okay. So for any polynomial worst case, where p of n is some polynomial, ax squared plus bx plus c, or k sub 0, x to the n, all the way down to base of 1 or base of 0, those are polynomial time. You only really need, in the worst case, to look at the highest power in that. So if it's an n cubed, everything else goes away. Doesn't matter that it's 3n cubed plus 4n. It's an asymptotically worst case of n cubed. So when you talk about non-polynomial time, n is exponential time, 2 to the n, or 3 to the n, or really k to the n, or n to the k. Those are just, they don't work. They don't scale. So in these days where we're talking about larger and larger data sets, you can't scale those types of routines. So you have to go back to the drawing board and redesign your algorithm, probably making use of more memory or some sort of a heuristic to make your algorithm run in something that's polynomial time. This is the basis of n versus n, pn, right? pnn. We're not going there. So let's do a couple of examples where we look at the complexity of algorithms. This was already on the slide. This has nothing to do with the fact that we're on the quarantine. Okay, so here we are. This is my standard find max element. This is actually a problem that you've done in 160 in basic C programming, finding the largest value in an array. And if we look at the number of steps, we can look at 2 different types of operations: the comparison in the if and the assignments. Okay. So the assignments, by analyzing this, we can say that this is going to do 2 assignments to max. It's going to assume at the top that the assignment is correct in the first, and then it is going to run through how many times through this loop? Well, it's going to have to look at every single element. So it's going to make n comparisons, array sub I greater than max. So it will run through the length, which we count as n. Okay. So the fact that we do 2 assignments would be n plus 2. So that's comparisons is going to be n, and then 2 extra assignments. But again, in the asymptotic, the worst case, we don't care about any extra constants or any multiples. So this is a linear time. The number of steps is about n. Questions on how I did that analysis? Okay. Here's another one. This is using a array, but what it's doing, what is it doing? It's looking at the number of places where there's an inversion, okay? An inversion is basically this element is greater than that element. And specifically, what we do is we say, okay, for I equals 0 to the length, for j equals 0 to the length. Then we look and we say, okay, is array sub I greater than array sub j? Now, the second time through the loop, we're running actually one less because we start at I plus 1. Okay? So in the grand scheme of things, this is going to run through the top loop n times, the inner loop n plus 1 divided by 2. Okay, that's how you get the sum of 0 plus 1 plus 2 plus 3 plus 4 all the way to n. It's n plus 1 divided by 2. But at the end of the day, this is really n squared. If you multiply the n through, you'll get n squared over 2 plus n over 2. That's polynomial time, but it's n squared. Everything else, throw it away. And in fact, you could have known that just by looking at this. 2 nested for loops, n squared time. This feeds directly into the idea that I was telling you about earlier, I don't know, 2 or 3 classes ago. The number of tabs you have in your program in a particular function is a good metric for how complex your algorithm is. Because every time you have a tab, it's usually either a conditional or a loop. So if you have a bunch of loops nested inside of each other, that's going to be a complexity. Usually the number of for loops nested inside of each other is the coefficient, or sorry, not the coefficient, the power. Why can't I think of the right math word for power? Exponent, the exponent. Okay, so let's look at this. This is a program that takes a bunch of numbers and calculates the sum of their cubed roots. And it should be no surprise, 3 for loops nested inside each other, all running the same number of times. The inner loop, C loop, is going to run n times. The outer loop, B loop, is going to run n times. But every time B runs, it runs all of C. So that's n times n. And then the outer loop, the A loop, runs the B loop n times. So now you've got n times n times n cubed. Okay. This example, it's not quite so clear-cut. Okay, we have 2 different numbers, n and m. But at the end of the day, this is quadratic time. Okay, it's n times m. So for like-sized n and m's, if they're in the same order of magnitude, you can assume that n is basically the same as m as n squared. Now, depending on what type of analysis you're doing, you might leave it as n times m, or you just say it's n squared. So it depends on if you know whether or not n and m are going to be in the same ballpark. Okay, even when you start putting things like nesting of if statements, it becomes a little more difficult to analyze. So this is constant. It's going to do this summation operation every time through the loop. Here, it's only going to run some of the time. So you have to make a decision of how often this inner loop is going to run. So for this, it's only going to run one time for every run of x. So it's only going to run when x and y are equal. So depending on whether n or m is smaller, that'll tell you how many times it's going to run. So when you look at this, it says, okay, n times m plus min times n. But I sort of disagree with, well, actually in this case I don't disagree. So it's going to run n times some constant. So this is n squared. This is some constant times n. You could make a case that this might be cubic time, but I think we've done enough of that. Okay, now we get into things that are very, very bad. For a given number n, What does one shift? Go back. What does one shifted left by n really mean? When you take 1 and shift it over 0 places, you're left with 1. What happens when you shift 1 over by 1 place in binary? What does that give you? It gives you 1, 0 in binary, but what's 1, 0 in binary when you convert it to decimal? No, it's not 3. You're not leaving the 1 there. You're taking the 1 and moving it 1 place over, so it's 2. If you take that 1 and you move it over 2 places, then you've got 1, 0, 0. What's 1, 0, 0 in decimal? 4. Yes. And we could go on from there. It's 1, 2, 4, 8, 16, 32, 64. That's basically taking 2 to the power n. So this is taking the sum of all numbers between 1 or 0 and 2 to the n. And it runs in n squared time. If you increase n by 1, you're going to double the length of time it takes. Now this is a trivial example. It's pretty self-explanatory what it does. Same with things like factorial. Now this is an example of recursion, which I don't cover in 264. I'll let ECE264 cover that, which electrical engineers, you'll be happy to know you don't have to take. But here's the thing, that for a given n is going to run many, many times. Okay. What? Oh, okay. So this is talking about its linear runtime, which, yes, it does take n steps. It takes n and then multiplies it by the result of something. But it actually, it's much more complicated than that because it's going to be allocating a bunch of stack space too. So memory complexity, this is pretty rough. But linear time, I guess I can get behind that. The Fibonacci sequence runs in exponential time. This is another recursion, but this is worse. And the reason it's worse is because it's not done well. It's very easy to understand. Okay, this example of the Fibonacci sequence has 2 base cases for n equals 0 and n equals 1. Return 1. For anything else, figure out what the previous 2 things were. This is not a good runtime because it's going to calculate things multiple times. When it calculates Fibonacci of 2, for example, it's going to say, okay, give me Fibonacci of 1 and Fibonacci of 0. So it'll go back, it'll return 1 for both those first 2 cases. When it tries to do Fibonacci of 3, it's going to have to recalculate Fibonacci of 2. Well, it would be better if it had stored that. Could you write this as O sub n? If you, yeah, there's definitely better ways to do that if you don't use recursion. Fibonacci, similarly, you could write this as a time complexity of O. So could you do it as n or log n? I'd have to look at that real quick. But definitely this is not a way that you want to do it because it runs in exponential time. Definitely if you use the hash set, you would be a lot better off. So I think that's the next lecture. We're going to talk about how do we compare different types of data structures. And this is the summary right here. Okay, this is how we use different types, and also I think we go on to hash tables. And you can see here that the dictionary, part of the reason I use the dictionary is because it's constant time to add or find or delete. Compare that to an array or a resizable list. They're at best case constant time, but at worst case linear time. So hash tables are definitely a lot, or well, dictionaries, definitely a better thing. So we're going to pick this up on Wednesday because I'm actually over time. Okay. In the meantime, you should be starting your code base. You should be getting full on to that. If anybody has not yet sent a link to the TA with their group repository, please do that. If you're having trouble making a Private repo, please make sure that you have signed up for an academic account. It is like automated. You just type in your EDU email address and you don't have to pay $8 a month. You get free, unlimited private repos last time I checked. Is that still true, Tim? I will let Tim, I don't want to like put out Tim's username in like public YouTube land, but needless to say, he will be in your exam because he was the one who made the push to your exam. So just check your exam's latest push and you'll see his username, okay? All right, that's it.